lamina. We will now consider the thin plate of constant mass density delta occupying the region under the graph of f on the interval a, b, where f is a positive continuous function. The objective is to locate the center of mass of the thin plate, called the centroid. We will accept the two principles. The symmetry principle states that if the region R is symmetric about the line L, then the centroid of the region lies on the line L. And the principle of additive of moments, meaning that if we were to decompose the region into smaller non-overlap regions, then the moment of the region is the sum of the moments of the smaller regions. Suppose we have the positive function f, which is above the x-axis, and the region from A to B under the curve f. Suppose this region represents the lamina, and we're interested in the centroid of this lamina. Recall that the center of mass x bar is the moment about the y-axis divided by the total mass, where the moment about the y-axis is the sum of the product of the mass times the directed distance to the y-axis, and y bar is m sub x divided by the total mass, where the moment about the x-axis is the sum of the product of the mass times the y-coordinate, which is the distance to the x-axis. But this lamina is not a system of particles, although we can assume that there are infinitely many particles of constant mass. We then slice the thin plate into n subinterval to obtain n rectangles. An I representative rectangle has the center of mass as xi bar and 1/2 y bar, or 1/2 f of xi bar. This is justifiable because the rectangle is small enough and it has the constant mass density. By the symmetry principle, the center of mass is right at the center. Thus, the center of mass of the ith rectangle is xi bar and 1/2 f of xi bar. But we're interested in the centroid of the lamina, or the center of mass of the thin plate. We first find the moment about the y-axis of the ith rectangle, denoted by m sub yi for the ith rectangle, and this is the moment about the y-axis. It is the product of the mass and the directed distance to the y-axis using the x-coordinate. This is the mass times xi, but the mass is the density times the area, A, but the area is the height times the thickness. The height is f of xi and the thickness is delta x. Rearranging this, we have delta times x sub I times f of xi times delta x. According to the principle of additive of moments, the moment about the y-axis is therefore the sum of all of these moments, so m sub y is the sum as I go from 1 to n, delta xi times f of xi times delta x, but as n goes to infinity, this is the definite integral from a to b, delta x f of x dx, where f is a continuous function. Similarly, the moment about the x-axis is the mass times the directed distance to the x-axis using the y-coordinates. The mass is the same, the density times the area of the ith rectangle, but the directed distance is now 1/2 yi, where 1/2 yi is at the center of the rectangle. This is delta times f of xi times delta x for the area times 1/2, and yi is f of xi. Simplifying this, we have 1/2 times delta times f of xi, the quantity squared, times delta x. The moments are additive, so the moment about the x-axis is the sum as I go from 1 to n of 1/2 delta times f of xi squared times delta x. And as n go to infinity, we obtain the definite integral from a to b 1/2 density delta times f of x squared dx. This is the moment about the x-axis. We have the moment about the x and the y-axis. We still need the total mass, where the total mass m is the sum of mi, but mi is delta times the a sub I, but a sub I is the height times the thickness, so this is delta f of xi times delta x. And as n go to infinity, this is the definite integral from a to b, delta f of x dx. This is the total mass. Once we have these three quantities, we can find x bar and y bar. They are now in the form of integrals. X bar is the moment about the y-axis divided by the total mass, and y bar is the moment about the x-axis divided by the total mass. Observe that if the density is constant, we can move the density outside of the integral and cancel out delta. The denominator is now simply the integral from a to b f of x dx, which is the area. Thus, if the density is constant, x bar is 1 over a times the integral from a to b x times f of x dx, and y bar is 1 over a, the integral from a to b 1/2 f of x squared dx. If the density is not given in the problem, then we should assume that the density delta equals 1. What we computed is called the centroid, or the center of mass.